Okay, so as the title of this slide suggests, we are going to be talking about switches, how they relate to logic gates, and we are going to try to design logic gates using transistors. So we are going to see how these three elements of a digital circuit play together. So let's get into start simple, right? Let's see what a switch is. Well, a switch essentially has the job of either connecting 2 points. In this diagram, we have point A and point B, um, or disconnect them. So when we connect them, so if you see this diagram over here, that's a switch symbol. And when the switch is closed, that means it is connecting A and B. It is supposed to be, it's called a closed switch or a on switch. And the other position could be open switch or off, corresponding to an open circuit between those 2 points, which means there is a disconnect and no current can flow between those 2 points. So that red arrow over here, let me erase these two and talk about the red arrow. The red arrow over here shows the direction of that switch toggling from an open state to a closed state, or an off state to an on state. And we have seen mechanical switches in the daily life. This is an example of somebody turning on and off, say, a light bulb. So that's a mechanical response. Switches could be in the form of slide switches, push buttons, or toggle switches. They come in a variety of forms. But we are trying to do this switching at very fast speed. And the type of switch that allows us to switch between states on and off very quickly is an electronic switch, for which I don't have to stand there and manually flip a switch on and off. I'm going to essentially control one of these terminals so that the current flows or not, and the switch is turned on and off. The electronic switches mainly come in two forms. The first one is a BJT, a bipolar junction transistor that we are going to be using for our class. And we also have a faster response time, a high speed switch uh, called the MOSFET transistor. MOSFET stands for metal oxide semiconductor field effect transistor. So we'll be looking at BJTs for experiments 6 and 7. So the first thing we are going to look at is a circuit model of an identity function. So the simplest function that I can think of that operates on binary signals. A binary signal is a one that has two states, on off, low high, 0 1, is an identity function, the simplest function. What is an identity function? Well, um, there's some sort of a digital circuit which takes in an input X and gives you an output y, and if y equals x, that's an identity function, also called as a buffer. So there is some use to this, but it might seem, at the beginning of this discussion, it might seem useless, but there is a use to this. So how do we build this model using sort of the components that we know in a lab setting? So to talk about the identity function, I have a DC voltage source as Vs. I have a switch that could be in either an open or a closed position. And I have a light bulb that could either turn on or off. I'm using RL to represent the resistance of the light, and I'm using IS to represent the current flow through the light from the voltage source. I'm using X to represent the state of the switch. It could either be open or closed. And I'm using a binary variable Y to represent the state of the light bulb, on or off. So let's try to build up a table and look at the two scenarios over here. The switch could either be open or closed. And when it is open, we have a break in the circuit. No current is going to flow through the loop. and the light bulb is going to be off. When the switch is closed, we are allowing current to flow through, in fact, of the amount of Vs divided by RL using Ohm's law, and the light bulb in that case is going to turn on. And now, using this sort of a table that we can easily read, let us try to map that to a different table by associating open and closed with a 0 and 1. I'm using 0 for open, that means that the switch is not connected or off, and I'm using 1 for closed switch, which means it is on switch. And similarly, I also have a mapping for the output here. The light bulb is off and on, represented by a logic 0 or a logic 1, a false or a true, a low or a high. And if I do that mapping, I come up with a table, and this is called a truth table. Binary inputs X and Y. X is the state of the switch, Y is the state of the light bulb. On the input side, I have 0 and 1, and as you can see, Y is 0 and 1, corresponding to off and on when the switch was open and closed. And if I compare all the entries, Y equals X for all the combinations of X. And because X is a binary variable, I'm only going to have two possibilities over here. That gives me the logic expression for this identity function. The output at Y is going to equal X. So that's my logic expression. The symbol for a buffer is simply a triangle. X goes in, Y comes out. Both input and output are binary in nature, and the buffer, the symbol of the buffer, is simply a triangle. So that's essentially the simplest logic function one can implement. And we can model this function using three elements: a voltage source, a switch, and a light bulb. All right, now let's move on and talk about this low and high in the context of the voltages that we are likely to see. So for CMOS transistors, this is complementary MOSFET transistors, what we have is a low level which is going to be represented with a range of voltages. Any voltage between a 0 and a 1.5 is going to be considered for CMOS to be a logic 0 or low level. And any voltage between 3.5 and 5 is going to be considered a logic 1 or a high level. And clearly, because there is a range of voltages that are low and high, we also have a range between 1.5 and 3.5 volts where we do not have an associated binary level. So the voltages that fall between these two levels are going to be undefined. So those go in the middle. It's unknown whether it is a low or high in that case. Now clearly, because there is a range of voltages, not every voltage is treated the same way. So if I look at 0 volts corresponds to a 0. However, this is going to be a strong 0, strong logic 0. And as I go up and very close to 1.5 volts, I have a weak 0 because it's getting to that particular range of confusion. And in the other case, for the high level, I have a strong 1 here and I have a very weak 1 here. So briefly, the purpose of a buffer is to translate a weak 0 or a weak 1 into a strong 0 and a strong 1. That's essentially what we are going to use a buffer for. And we'll see that with some examples. Now let's talk about the next logic function, and we are still looking at the circuit model. We still have a voltage source. We have added a series resistance RS here. We still have a switch. We still have the light bulb. However, we have changed the position of this switch. It was earlier where RS is, now it is in parallel with the light bulb. And with this new model, if I lay out a similar table which monitors the state of the switch with input X, current I1, which is flowing through the switch, current I2, which is flowing through the light bulb, and the state of the light bulb represented by the output variable Y, I have still true entries because the switch again can be in one of those two positions, on or off, open or closed. So when the switch is open, no current can flow through the switch, so all the current will have to flow through the light bulb, turning it on. And in this case, I2, the current through the light bulb, will be Vs divided by the sum of these two resistors because they will be effectively be in series. Now in the other case, when the switch is closed, my circuit diagram is essentially going to be Vs, Rs, and the switch. The light bulb is not going to get any current because we have a path of least resistance over here. So Is is going to be Vs divided by Rs. However, I2 is going to be 0 because no current will pass through the light in this case, and the light bulb hence will be off. Now if I map this to a truth table, I have X for the switch and Y for the light bulb. When the switch is open, the light bulb turns on. When the switch is closed, the light bulb turns off. So it's exactly the opposite of the input, hence the NOT functionality, also called as an inverter. Logic expression for the inverter, we simply use a bar over the input. So X complement or X bar or X prime, that is essentially the NOT functionality. We are going to try to write things in this form. You may also see it in some of textbooks represented as this in the other two forms. The symbol, input on the left side, output on the right side. We still have binary input and binary output for X and Y respectively. And we still have the triangle, which was the buffer, but we have a bubble in front of that buffer, which the bubble is what signifies inversion. So that's your NOT function. Now with having learned the identity function, the concept of the concept of buffer and the concept of the NOT gate, let us try to design something. So let's say we have a design task. We have two systems here, S1 and S2, and I'm going to show you two variations of this. So we have S1 and S2 even here. I'm just going to separate this out a little bit more. So the challenge is connect the output of stage 1 to the input of stage 2. That's it. That's the goal. So for both versions of my solution, I'm going to look at simply that task. Connect the output of stage 1 to the input of stage 2 so that there is a cascade, there is a series connection. And I'm going to assume that the kind of signals that we are going to be transferring from one stage to the other, they are binary in nature. So they have low and high levels. So let's say if we give this task to two students, let's say student X and student Y. Student X says, you know what, I'm just going to connect that right away and I'm done. So if I wanted the output over here to be the same as the input over here, then I will just connect them with a wire and I will be done. That's the solution offered by student X. However, student Y says, I am not going to do that. I'm in fact going to use a buffer in the middle because the output equals the input in this case. And a buffer is in reality implemented by using two NOT gates back to back. So for example, a 0, if it goes in, it becomes a 1 and it becomes a 0 over here, which means these two are equal, y equals x. Or the other option is if 1 goes in, it is 0 over here and 1 comes out over here. Again, they are equal on the edges. So output equals input. So that's how we implement a buffer by using two back-to-back NOT gates. So student Y takes this approach and student X takes this approach. Well, one is going to be better than the other. And here's the reason. So if the output of stage one, say, becomes a weak logic level, say over here we have a weak signal, weak 0 or a weak 1, then during this transition, or if you have more things connected to the same spot or the same output of stage 1, you might not get a strong enough input of that logic level into stage 2. So that's a problem. If it was a strong signal here and these were not there, you'd probably be okay. Strong logic level goes to the next stage. However, that strong level will be divided among different loads, S21 and S22. If we are connecting multiple things over here, then essentially what we have is these are going to operate as parallel loads to the same voltage, which means that it will be that voltage, whatever is over here, which was strong, will need to be divided. And we know that voltage division leads to reducing of that voltage. So each one gets a smaller voltage, which is definitely going to make it weak at the input of stage 2. So that's a problem. So student X solution is simple, but it has some problems. Student Y is going to be okay. The reason is the buffer is going to regenerate that logic level. So even if a weak input logic level goes in, a strong logic level comes out. And we'll talk about how the buffer does that regeneration of that logic level in a few moments. If you have parallel loads, would you put buffers on each branch? No, that would not help, because if you have buffers on each, well, it will help to some extent. But if you have too many loads, then we do not have a way out. It might become too weak for it to be able to be regenerated. So there is a limitation, which is essentially called a fan out limit for logic gates. How many things can you connect to the output of a gate? There is a limitation. Maybe three things or four different inputs you can connect to output of something. Similarly, there is a fan in limit. The number of things you can connect to the input of a logic gate, or the number of things you can connect to the output of a logic gate. So your question is a very good question, Derek. How can we use a buffer in each branch of the parallel loads? The problem with that is if you have too many loads over here, it might be too weak. It will become too weak. The more number of outputs you have, the lesser voltage each one is going to get, which means that it might be too weak for the buffer to recognize it. So we may get into a problem of not being able to recognize it. So it essentially amplifies I would not call it amplify, I would call it regenerate. Um, yeah, so it's not amplifying or reducing. I would use the terminology of regeneration. And when we go in and look at what is inside this buffer, which is going to be sort of a transistor based circuit, then we can probably see how that will work. But I would try to avoid the term amplification over here because it's not the same meaning. Okay, let's go ahead and talk about AND function. So this is the next logic function in our series of logic functions that we have been looking at. Again, we are looking at a circuit model. So how would you sort of build a model for an AND function? And you could probably do this if you have a room where you have two switches controlling a light. This is probably not the right one, but you probably have seen something similar to this at your home. So for AND, what do we have? We have two switches, and the keyword over here is going to be series. Two switches that are in series, or for that matter, any number of switches that are in series will give you AND functionality. Because for the light to turn on, switch 1 has to close and switch 2 has to close and switch 3 has to close. All the switches have to be closed. Only then the light will turn on. If even one of them is off or open, the light will be off. So the key word here is for AND logic function, we have switches that are in series. And if you take a look at the same sort of a truth table for AND, only when both switches are on or closed, only then the light comes on. Even if any one of them is off, the light remains off. So both this and this have to be true in order for the output to be true. Logic expression, we use a dot symbol to represent AND function. So x1 and x2 is the output one. So this is the one that we are going to follow. Some textbooks follow this or even this. But I prefer writing it very explicitly as x1 and x2 in the first form. Next, what is the symbol of an AND gate? AND gate has a D symbol. You have the inputs, in this case, two inputs on the left side, and you have one output, which is also a binary output on the right side. Now notice over here one difference between the previous two functions, identity and NOT gate, and AND gate is that identity and NOT had only one input and one output. However, AND can have three and even four input, one output gates. And like I said, there is a fan in limit because of voltage ranges and the fact that we have weak logic levels and strong logic levels. We will have a limitation on how many things you can connect to the input of a gate. 2 is probably going to be okay. 4 and 5, probably we are in danger. So that means a weak logic level will get corrupted. Or even a strong logic level has a chance of getting into the undefined region. All right, let's move ahead here to an OR function. For OR, things are going to appear in patterns over here, like series and parallel and on and off and OR, identity, not. So like a two sides of a coin situation. So for OR, we are going to need switches in parallel. So if you have two input OR gate that I'm representing over here as two parallel switches, X1 and X2, still have the voltage source, still have the light corresponding to the output. Even if one of the switch is closed, I will have current flow and light will turn on. That is represented in the truth table as this. Even if one of them is on, the light will turn on. Both have to be off for it to be off, for the light to be off. Logic expression, the plus sign is what corresponds to an OR function. So x1 plus x2. And the symbol, very similar to the buffer. However, there is an arc in front of that triangle. So instead of having a simple triangle, we have an arc at the input side. This is a 2-input OR gate. Again, you could have a 3-input OR gate. Again, the fan-in limitation will apply, but we will always have a 1-output logic gate. So that's as far as OR gate is concerned. A quick recap. What do you need to take away from this discussion so far? OR switches in parallel and switches in series. Not switch in parallel with the light bulb. Buffer or identity switch in series with the light bulb. So that's sort of a quick summary of what are essential concepts so far. Okay, let's move forward with the NAND function. Now, because we have seen NOT and we have also seen AND, we can combine these two functionality. Actually, it's probably better if I write AND first, because NAND equals AND followed by the NOT function. So NAND is exactly the opposite of AND. So the symbol is D followed by that bubble that signifies inversion. So I can actually break this down and write an equivalent symbol, and followed by a NOT, x1, x2, and y. So that's NAND, or not of AND. So what is the circuit model? Well, because we have AND, we need switches in series. So still, we have switches in series situation because of the and because we have not of AND, that particular combination of series switches is in parallel with the light bulb, exactly the same way we did for NOT function. When we draw up a truth table for this, we have got x1, x2 as the two inputs. By the way, we are talking about two input situation, which is why we have uh, 4 possibilities between x1 and x2. In a general case, so for example, if you had let's see, if you had m inputs, m binary inputs, how many different rows would you have in this truth table? Well, you would have 2 raised to m, where m is the number of inputs. You would have m because of the number of inputs, and you would have 2 because we are operating on binary inputs. Binary inputs can have 2 levels. Now, the next question, which is very useful, is there a particular pattern that I can use to fill the input side of my truth table? For the output side, I need to know the logic function, but for the input side, there should be a pattern, and there is. The rightmost column of the input simply alternates 0, 1, 0, 1, 0, 1, and so on. The next level up, in this case x1, goes like this: two zeros, two ones, two zeros, and two ones, and so on. The next level up, if we had a 3-input situation, would go four zeros, four ones, four zeros, four ones, and so on. One level above that, it would go 8 zeros, 8 ones, 8 zeros, 8 ones, and so on, and so on, and so on. So I hope you see how to quickly write up all the possibilities that go in the input side. This trick is very handy when you try to write a truth table. So for example, for a 16 input truth table, this trick comes very handy. Did anybody have a question here? I heard someone. No? Okay. Let's see. So we talked about that. We talked about that. What is a logic expression? Well, for AND, we simply had this. For NAND, we are going to add the bar over it. So the bar is going to be on both x1 and x2 combined. Guys, if I can request you to turn off your microphone, that would be great. I'm I don't know who that is. Let's see here. I see it now. Okay, so we should be fine. All right, let's continue. So x1 NAND x2, let's see, can also be written in this form, can also be written in this form, but I really don't like this form, and the reason is this. You know, it's neither here nor there. So, you know, where does it start? Does it include x1? Does it not include x1? There's some confusion there. So what I like to write is this: x1 and x2 parentheses and bar over it. So that's a clear NAND function. Next, what is a symbol? We talked about this. A D followed by the bubble. The bubble is signifying the inversion. Yes. Yes, Corey, I did. Next, let's talk about an interesting question here. X1, X2, is it equal to that? So on the left side, we have complement X first, complement X2, complement X1, complement X2, then do the AND between them. Is that going to be the same thing as ANDing them first and then complementing them? Absolutely. You're right, Derek. The answer is no. And the way you can quickly check this, or things that are similar to this, is by quickly putting things in a truth table. So I have x1, x2, and I have x1 complement, I have x2 complement, I have x1 complement and x2 complement here. And let's say my last entry is NAND. So let's quickly go through this to verify. Note, all the entries need to be equal for it to be equal. So because I have, actually, let me erase this because they are both inputs here. 0, 1, 0, 1, and then I got two zeros, two ones. So those are my four possibilities. X1 complement is going to simply be 1, 1, 0, 0. X2 complement, or not x2, is going to be 1, 0, 1, 0. I need to AND these two guys next. Both are 1. Good. bad, bad, and bad. The last column can be obtained by first ANDing the inputs and then flipping the output. So if you see here, AND of this is 0, flip it, you get a 1. AND of the next one is a 0, flip it, you get a 1. AND of the next one is a 0, flip it, you get a 1. The last one will give you a 0. And as you can see, good over here and good over here. However, it does not equal here and here, which means this is not equal to that. Alright, so let's move on with our discussion here. We talked about the circuit model of NAND. Similarly, we can talk about a circuit model for NOR. In this case, because we have OR, we are going to have switches in parallel, and we do. And because we have NOT, that particular configuration of switches in parallel is going to be in parallel with the light bulb, just exactly the same way as we did for the NOT gate. What is the truth table going to look like? We still have the 4 entries of x1 and x2. We have y, which is the output. It is the opposite of OR. So OR would have given us this or this, right? 0, 1, 1, 1. But because it's the exact opposite of OR, it is giving us 1, 0, 0, 0. Logic expression. First do the OR, then do the NOT. Symbol. OR gate followed by the bubble inversion. That's going to be your NOR gate. Okay, I think this is good for the NOR gate. We have a few more. In fact, we have two more logic gates that we are going to talk about. Exclusive OR is next. Exclusive OR function is similar to OR, but we are going to change when the inputs are mutually exclusive. So for example, if I look at the truth table of exclusive OR, still have a two input situation, x1 exclusive OR x2, and note the difference in the symbol. You have a circle over the plus sign. The plus sign for OR, the circle to suggest that it is slightly different from an OR function. It's an exclusive OR operator. Only when both the inputs are different, the output is a 1. When the inputs are same, the output is a 0. So exclusive OR gate is also called as a inequality detector because of how that truth table looks like. It is detecting when inputs are different by giving an output of 1. The symbol, similar to an OR, but we have an additional arc at the input side. That's exclusive OR. Now let's try to write a logic expression for exclusive OR. It turns out it is not as simple as we have been writing for the other gates so far. Exclusive OR, the function you can write by using this technique. Notice where the ones are in the output column. In the output column, I have ones at two different locations. So let's call this Y. Let's call this x1, let's call this x2, let's call this y. The output y is 1. Y is 1 when x1 is 0 and x2 is 1, or x1 is 1 and x2 is 0. So let me highlight these to suggest which row they are corresponding to. So the first one corresponds to yellow and the next one corresponds to the blue statement. And I can represent or capture these two statements in a logic expression. X1 exclusive OR X2 is X1 and X2 complement, or X1 complement and X2. So if I try to do that same mapping again, X1 is 1 for the blue, which is this term right here. And for the next one, I have yellow. So I've color coded the statement, the rows in the truth table, and the terms in the exclusive or logic expression. So that's your inequality detector, the exclusive OR gate. We have one more gate. Let's actually do this. Let's copy paste this and make quick changes to this, because the last gate in our discussion is going to be very similar to exclusive OR. We are simply going to have everything reversed. So we have exclusive NOR. So I've changed this guy over here. Next, do I need to change the symbol? Yes, I have an inversion. So I'm going to put a bubble in front of that. In terms of logic expression, NOR means I need to add a bar over the entire thing. I still have the plus and the circle as exclusive OR, but I'm going to flip the entire output. Next, the entries were 0, 1, 1, 0. Now they are going to become 1, 0, 0, 1. Instead of an inequality detector, it is going to be called an equality detector, because it gives an output of 1 when the inputs are equal. Next, the statements slightly change. Let's go back and highlight them as yellow and blue. And my statements will change here. 0 and 0, 1 and 1. Which means the top statement is both 0, so that's yellow. Oh. And the next statement is corresponding to both being 1, so that's your blue. The last thing, let's adjust the logic expression. I have a bar over this because it's exclusive NOR. I'm going to have a bar on both and bar on none. The first one corresponds to yellow and the next one corresponds to blue. So that's your equality detector or the exclusive NOR gate. Truth table, symbol, logic expression. Alright, so what we are going to do now is take a break and come back with a discussion on transistors. If you guys want to grab something to eat or drink, take a quick break and let's be back at 5 p.m. So right now local time is 4:49. Let's be back at 5 p.m. So a 11-minute break starting now. I will leave the WebEx session open so you guys can stay here, but just be back in 10 minutes.